Suppose we have a string of length L that we want to shape in the form of a rectangle, and we want to find the dimensions of the rectangle that maximizes its area. So let's call this side of the rectangle X, this side Y. So this in turn becomes X, and this becomes Y. So the string has a length of L. Now if we're going to shape it in the form of a rectangle, that means that the perimeter of the rectangle has to equal L, has to equal the length of the string. So perimeter of rectangle equals L. That means X plus Y plus X plus Y equals L. That's 2X plus 2Y equals L. And if we divide by 2 this entire equation, then we have X plus Y equals L over 2, and let's call this equation number 1. So the area of a rectangle is just its width times its height, so it's X times Y, and let's call this equation number 2. So X and Y cannot change independently. They're tied by this equation that the sum of X plus Y has to equal half the length of the string. So from equation 1, we can write Y in terms of X. So Y equals L over 2 minus X. And let's call this equation number 3. And so what we're going to do now is substitute equation 3 into 2. So 3 in 2. That gives us A equals X times L over 2 minus X. And we'll call this equation number 4. So equation number 4 shows us that the area is just a function of X. So once we know X, we know the area of the rectangle for that specific value that we selected. So we want to find the value of X that maximizes the area. So how can we do this? So let's take an example here. Let's say L equals 16. So that means X plus Y from equation number 1, that X plus Y equals L over 2. So X plus Y equals 8. So let's select a couple of values for X and Y, and let's find the corresponding area. So if we were to select that X equals 0, that really ends up not being a rectangle, but just kind of a straight line. So the value of Y would be equal to 8, and then the corresponding area would be 0. So the rectangle has essentially collapsed down to a straight line. If we selected X equals 2, that means Y equals 6, and then the corresponding area would be 12. If we selected 4, then Y would be 4, the area would be 16. If you moved on to 6, Y would be 2, area would be 12, and if X equals 8, Y would be 0, the area would drop down to 0 again. So if we plotted this, it would look something like this. So as a function of X, and this is the area as a function of X, the area starts at 0, it goes up, and it's going to go down again when X equals to 8. So we want to find this value of X here that gives us the maximum area. So how can we do this? So this is an optimization problem, and we're going to solve it using calculus, using differentiation. So let's draw this again here. So X, A of X. So we have a function. It's actually a quadratic function, so if we expand this, Y equals X times L over 2 minus X squared. So it's actually an inverted parabola. So this is how our function looks like. So if you remember, if we take the derivative of A with respect to X, the area is a function of X, this is the rate of change of A with respect to X. dA by dx, that's the rate of change of A with respect to X. And it has a geometric interpretation, which is if we pick a point here, then dA by dx is actually the slope of the line at the point that we selected. So if this is x, then dy by dx is the slope of this line. So dA by dx is the slope of the tangent to the curve at this value of the function. So let's draw this here. So here let's try and plot dA by dx. And let's just try and align this. So if we look at this part of the curve, if you stand at any part of this curve and you take a small step to the right, you'll find that the function increases. So if I'm standing here, if I move to the right, you'll see that the area increases. That means that dA by dx has to be positive in this region. On the other hand, on this side of the curve, if you were to stand here and take a small step to the right, you're going to find that the function actually decreases. So the slope of the function has to be negative on this part of the curve. Now somewhere in between, this slope has to cross 0. I mean, we'll show it's going to be a straight line, but dy by dx is going to be something like this. So on one side of curve, dA by dx is positive because the function is increasing. On the other side, dA by dx is negative because the function is decreasing. But somewhere here in between and exactly here, where the slope becomes equal to 0, we'll find that dA by dx equals 0. So dA by dx, when that equals to 0, that corresponds to the maximum of the function. So the way to solve this problem is we're going to take the derivative of a with respect to x, set it equal to 0, find out what this x corresponds to that makes the derivative equal to 0, and that's going to be the width of the rectangle that maximizes the area. So let's do this. So we have dA, we have here, let's call this equation 5. So we have a as a function of x. So dA by dx equals, L is a constant, so L over 2 is a constant, multiplied by x. So derivative of this term with respect to x equals L over 2. The derivative of x squared is just 2x. So let's set dA by dx equal to 0. So that gives us L over 2 minus 2x equals to 0. That gives us 2x equals L over 2, or x equals L over 4. And if we substitute back in equation 1, we'll find that y equals L over 4. So the dimensions of the rectangle that maximize the area are x equals L over 4, y equals L over 4. That means it's actually a square. It is a square. And you can see here, we didn't cover all the possible values, but you can see here that when x equal y equal 4, the area was 16, which was greater than everything else that we have here. So the answer to the problem is, if we have a string of length L that we're going to form in the shape of a rectangle, the dimensions of the rectangle that maximize its area is just to make that string make that rectangle as a square, and then all sides are equal to L divided by 4.